is a French engineer who studied first agricultural and in the food industry before branching out into computer science. Today, computer science teacher at Tiananmen State University. Since his childhood, he's been truly passionate with sciences and space, and for the last 10 years, he's been involved in devising a strategy for overall interstellar travel. He's a great proponent for change and in large scales of approach, more than just a crew, a space nation, more than just a spacecraft, but an interstellar arc. Bruno?
Thank you. Yes. Oh. So what you see in the screen is the Interstellar Arc. It's quite big, 10 kilometers long, 10 kilometers large, okay, for the hollow cylinder here, full of atmosphere, of course. But, okay, it's a world ship, and about the reason to build a world ship, we will speak it about during the hackathon, I think. But for this speech, I will speak about the bow, this mass, okay? It is mainly ice, and we will see why. The mass of the overall structure is about 400 gigatonnes. And the mass of the payload is only 20 gigatonnes. So that I want to show is why we need so many fuel at the bow, and a fuel which is not energetic fuel. It's only water. Okay, and this configuration, more than 95% of the whole vessel is water. Just a postulate for our work. No breakthrough, that is to say, of course, we need a breakthrough for fusion. If we have not fusion, nothing is possible. But okay, we say that to go from, to reach a distance d, we need to accelerate mass to a velocity v, under c, of course, and decelerate. That take an energy mv square, and the time is the relationship between energy and time is this one, and there is no way to do. There is no another way, okay? That's our assumption. And for us, just to say it, this is the best explanation of the Fermi's paradox. Second postulate, it's not no sail. Of course, it's physically possible, but we consider that light sail, photon sail, are solution only for light payload. Because if not, for a manned, for an interstellar arc, we need a sail of the diameter of the Earth itself. So it is a vessel driven by mass ejection. So the mass ejection is, to calculate the mass ejection, you use the Charkovsky equation. That is to say, the mass ratio need to increase the velocity from an initial velocity to a final velocity is, there is two parts in the right part. The first part is u, the exhaust velocity. That is to say, the relationship between the dv and u is linear, that is great. And the right part is the relationship between the mass ratio and the dV is exponential. I explain this because that explains why for all the astronautical context, in the current astronautical context, mass is the enemy because of this exponential relationship. But there is a little problem, which is the energy efficiency problem. If U is much greater than V, all the kinetic energy goes into the beam, into the gas, not in the payload. That's a problem. The first solution is optimize U. That is to say, U remain constant, but we give it a value which is a constant for the acceleration stage, which is 0.6275. Okay, this is the first way, and we can do better by varying U. That is to say, if we set U equal minus V, then the energy efficiency is 1. So you can do better. In this case, why it's 1? Because if U equal minus V, in the referential of the departure, the gas are at rest. That is to say, all the kinetic energy go into the payload and not in the gas. Yes? It's clear for everybody? In this case, this is not the Charkovsky equation, because Charkovsky equation is for U constant. So U disappear, and the final velocity is equal to the initial velocity magnified by the mass ratio. So in this case, the relationship between the velocity and the mass ratio is linear. It's great. But there is a little problem. That is because it's the depend of the initial velocity. If Vi is 0, there is a singularity, and the mass ratio tend to infinity. That's a problem. So we need a trade-off, and we will stage the acceleration. A first stage with U constant. So let's introduce V1 is the intermediate velocity, and we introduce R, a parameter. R is V1 equal R times Vmax. Vmax is the maximum of the velocity of the journey. R between 0 and 1. So in the first stage, R1, U equal, we optimize U by the first way. So you give to K1 the value of 0.6275. And when the vessel reach this velocity V1, the second stage begin, and U equal minus V, variable. Okay? This is the two first stage. There is a third stage which is deceleration, because we want to finish the journey at speed 0, of course, because it's a manned travel. But sadly, in this stage, during deceleration, V and U point to the same direction, so we can't optimize by varying U. So we optimize U by the first way, giving to U the value K3 times Vmax. K3 is not equal to K1, we will see. So this is the third stage, and we need a stage, I name it ballistic stage, engine off, of course, because we want to travel at the maximum velocity as long as it's possible. There is, okay, a little problem here. So there is 4 phases, R1, R2, B, R3. In this case, the overall propulsive efficiency is given by this formula, which is a function of the 3 parameters, R, K1, K3, okay? The overall efficiency is the ratio of the kinetic energy taken by the payload, NV square, and the overall energy expended during the travel. Okay, this is a study of the function of the efficiency with the 3 variables. So we see first when R equals 0, that is to say, we begin by varying U. In this case, the mass ratio is infinity, so it's a singularity. And in this case, the efficiency is 1 in 2.04. This is a maximum. We can do better. It's not 1 because there is a deceleration phase. And the minimum is when R equals 1. That is to say, there is no stage with U varying. And we can see that for all the value of R, K1 have always the same value. So it's not a free parameter. And K3 is in linear dependence of R. That is to say, it's not a free parameter too. The only free parameter is R. But R is not what is not very important. What is important is the mass ratio. So here we draw the curve of the energy efficiency to the mass ratio. So we can see that when R equals 1, there is no optimization by varying U. The mass ratio is 9, about 9. And the energy saved is 0%. And we can go to, if the mass ratio is infinity, the energy saved is 20%. So let's choose an intermediate value because we can't have a mass ratio infinite. So let's choose 20. And we save 10% energy. And this is the velocity curve. An important point is that we work at constant power. Okay, we have engine, and we expand the power of the engine are always the same, except during the stage B, of course. In this case, we can see that we are a first value of K, which is 0.63, okay? So we eject the gas at this velocity, and the and the velocity of the vessel increase like this. When reaching 0.5 Vmax, U become variable, minus V, and the increase of the velocity is linear. Then we travel at constant velocity, and then we brake. We decelerate. Just to see what, okay, it need, by this way, we need a huge volume of water. So an idea to collect water, because in the current astronautical context, mass is the enemy, but not now. Now it's the energy is the real problem. We can collect huge mass of water, for example, like this. We choose an acid asteroid, a Troyon-like. I think you know what is Troyon. It's an asteroid in the Lagrange point of Jupiter. Yes. And why we choose this one? Because it's iced asteroid. Because the asteroid in the asteroid belt are silicate or metal and few waters. So it's mainly water. Okay. The mantle of the asteroid is waters and CO2 and CH4 and NH3, etc. And silicate, metal, salts. Okay, let's imagine that we inject steam in the mantle of the asteroid, and we put the arc in a geostationary orbit for a radius of the asteroid of 15 kilometers and a mass of 10 power 16 kilogram, and a period of 10 days. Okay, the geostationary orbit is about 100 kilometers. So we have a space pipeline. It's not a space elevator. It's a space pipeline. It's more easy. It's much easy to build because it's only 100 kilometers, and the pressure is not so high, 10 bars. Okay, and to build the arc in a century, we need it's an assessment a flow rate of 10 tons by second. This is the arc. Okay, we can see the dimensions to have an idea, and it's a living structure. The other, okay, I couldn't develop all the arc, but the idea is to use the light atom of the solar system, CHON, to build a living structure. That is to say, the wall are vegetal fiber and waters, an ocean. And the fuel shield of an idea. And I will finish on this. It is the four stages of the journey, with the assessment of the value, the power. We take a power 10 petawatt. And the value of the velocity, the value Q is the flow rate. So we can see that we consume 84% during the first stage, because the the U is low, and we need a great flow rate. The thrust is about varying from 2.4 megaton to 0.4 megaton during the deceleration. And the acceleration is about a few kilometers by second by years. Okay, I think I will finish it on this point because the rest is for the hackathon.